upper extremity prosthesis and lower extremity prostheses. I'm going to start with lower extremity, probably spend about 2/3 of my talk on talking about legs, and then maybe the last third talking about arms. So let's start with a state of the art for legs. If you are and when there's different levels of amputation, but I'm talking about something called a transfemoral amputee, which means above knee. So your leg is amputated about here, and if your leg is amputated there, and you go to find a replacement leg, then this would be the state of the art that you would get. This is let's see, includes this part, which is a suction socket, and that's something that that holds the leg onto your residual limb. It's kind of like pushing your fist into a plastic cup, and then it's held on by suction. Except for this is actually molded to your limb. It has this little valve here, and so you push your leg in, and when you want to take it out, you can kind of push your finger into that valve and pull the suction socket off. So that connects this prosthesis to you. It has a knee joint. The knee joint is basically just a damper. This is a lot like the damper, let's say, on those doors or on a screen door, that when you throw it open, then it closes more slowly and smoothly. And then it also has this hard stop at the end, so the leg won't hyperextend beyond where it's shown right there. And so a lot of the time, the way that you keep it from buckling when you stand on it is just to make sure your weight is forward of the knee, and that will just lock it against this hard stop. The ankles are rigid, so it doesn't have an articulated ankle, and the feet are these little, usually carbon fiber leaf springs, so they deflect a little bit. But some of the salient characteristics of this is that you have, as I said, damping at the knee provides kind of smooth motion. You have the hard stop, which helps lock the knee when you're standing on it, and then these leaf spring feet, which give you a little bit of push off. So when you roll over that leaf spring foot and you swing your hip forward for the next step, then you get a little bit of stored energy in that spring. Some of the real limitations of these are that, most notably, is that the joints can't generate any power. So what that means is if you bend down with this leg, it's not going to help you get back up. You're going to get back up with your sound leg, assuming you're a unilateral amputee. Also, because they can't, another way to look at that the same limitation is that the joints can't move themselves. The only way I can move that knee joint is to take my hip and swing it around, and then it will swing in response to my swinging it. As far as moving that ankle joint, of course, I have to really put some weight on it because it's basically a spring, and that's the only way I can move it. And because of these limitations, this kind of leg, even though it is state-of-the-art, in fact, it has little microcontrollers in it that adjust the damping as you walk slower or faster, but still, it's really unable to reproduce healthy biomechanics, and it's very limited with respect to its ability to adapt to different activities and environments, and I'll mention some of that to you as we go. But some of the implications of that, amputees expend a lot more energy when they just walk in normal level walking, 60% more. They walk more slowly. They walk a lot less, probably about a third of what a typical active person might walk in a day. It's really hard to go upstairs in ramps, and that's because it doesn't have that power. And so when in healthy biomechanics you go up a stairs, of course, 1 foot at a time like this, they can't do that. The leg doesn't have power, so they step first with the sound side, and then they pull the other leg up to that stair, and they do it like that. If you're a bilateral amputee, then you're basically using your arms, and you're using handrails, and you're getting up that way. This is less intuitive, but stair and ramp descent is really hard. Gravity wants to accelerate you going down a hill. If you have kind of the snowball effect, so to speak, right? Gravity wants to accelerate things. In order to go down steps or slopes in a controlled and stable way, we do a lot of deceleration with our legs, but these legs, because they don't have power, because they can't move themselves, the joints aren't able to reproduce that normal biomechanics, and generally amputees tend to have much less control when descending stairs and ramps. In a similar vein, when just standing around or walking on uneven terrain, the joints don't have the ability to adapt to that uneven terrain, so people are much less stable. The result of this is that amputees fall a lot more than healthy individuals, and I'll pick up on some of that a little bit later, but amputees actually end up falling at the same rate as institution living elderly people, and they have to seek medical attention also at the same rate. And the problem is worse in younger amputees than in older amputees because they're more active. They go out and do more things. So we're trying to address all of these issues or limitations. And we're doing it by building, basically, a powered prosthesis. So in other words, a fully robotic leg, one that doesn't just have a damper and a spring, but reproduces the same capabilities that your neuromuscular system would be able to do. And one can ask why this hasn't been done before. And there are a few reasons. One is that up until just very recently, as in the last 2, maybe to 4 years, the robotics technology wasn't good enough to do what our legs can do in a package that's the right kind of size and weight. In other words, if you can make a leg that generates the right kind of knee torque and ankle torque and knee power and ankle power to duplicate what our legs normally do, but if that leg weighs 30 pounds, then nobody's going to wear it. So this was only recently, I'd say, again, very past few years, that some of the robotics technology has become good enough, and there are different reasons, market reasons for this, but that's become good enough to actually build something that performs like a leg in the same size as the leg and weighs essentially the same, a little bit less as a leg. The second issue is the control problem, in that before you had these devices that are rigidly attached to you, and all they could do, the passive devices, is react to what you do to them. So they're very predictable and controllable. A leg that has its own power like this can decide to do its own thing and start moving itself. So I could be standing here, and it can decide that I want to start running and start flapping around, and that's obviously unsafe and awkward. So one needs to figure out how to have this powerful robot rigidly attached to the person without any explicit means of communication, but to work cooperatively and reliably and naturally with the person to walk and do whatever the person wants to do. So our group has been working on this problem since about 2005, and I'll show you. I have to go there. I'll show you some of the work that we've done. So the first thing we did is build the device, and this I won't go into too much. This is the knee joint. This is the ankle joint. Here's a motor for the knee. Here's a motor for the ankle. It has this what we call a transmission. This is a ball screw. This is what we would call a slider crank linkage. And the whole point of this is because these motors will do 200 watts. That's about what your joints do when you're walking, let's say, upstairs or walking quickly. But it won't do the torque that you need. The torques that you need at your knee and ankle are much, much higher than this motor provides. And so you need a transmission to adjust the amount of torque that the motor generates to the torque that the knee or the ankle needs. Just by comparison, in your car, you have transmission, which adjusts the motor torque to the wheel torque, or motor speeds to wheel speeds. And those transmissions are at the most about 3 to 1. These transmissions are about 200 to 1. So we have to do this really big transmission, and it has to be, of course, light and small and not have much friction. So, but we have those units that these are the muscles, so to speak. As far as sensors, we have sensors that measure the angles of the knee and the ankle joint and how fast they're moving and how much torque the person's applying up here, how much weight is on the front of the foot, how much weight's on the back of the foot, how much torque is at each joint, and also the inertial accelerations of the foot and the lower leg in space. So that's kind of the sensor and actuator part of it and structure part of it. We have here, this is kind of the brain, so to speak. This takes all the signals and processes them, has a microcontroller on it that does all the control that we need to do, which I'll explain, and then sends all those signals out to the motors to make it do what it's supposed to do. This is not that important, but basically all this is to say is that we're able to build this device that essentially does what a leg can do and weighs what a leg that it's replacing would weigh. Okay, so now I'm at the control part. As I mentioned, control is really different, and it's really important because before you had these devices that can only react to you, and now you have devices that has its own power. It can both act as well as react. And so this, as I mentioned, it's a powerful 2-degree of freedom robot, and that's rigidly attached to you, but with no explicit means of communication. So everything the leg does has to be inferred. And it's obviously really important that this be stable and reliable because I'm relying on it for to hold me up, and prevent me from falling. We've developed a control methodology that seems to be effective for this, and I'll explain some of it to you. First, I'm going to explain it in the context of just normal level walking, and I took this. This is a slightly censored photo sequence from Edward Muybridge. Edward Muybridge is an interesting guy who was the photographer for the U.S. Geological Survey in the mid-late 1800s, and he left this long legacy, a great legacy of these sequential photos, which to us, with motion pictures now, seems like that's not a big deal, but then it was a big deal. And he has just sequential photos of a lot of things you could think of moving and doing different things. He actually started, I don't want to get too far off tangent on Edward Muybridge, but he started, if anybody has seen this picture, this was a standing bet that they had in the late 1800s about whether or not racehorses, all their legs left the ground at the same time. And so somebody commissioned him to do this sequence. He used, 16 different cameras to take this, and just used tripwires. And anyway, clearly all four legs leave the ground. So then this is where he started, and then he took sequential photos of lots of things. But anyway, this man walking is one of the things, somewhat crazy-looking man walking is one of the things he did. I wanted to use this to point out these salient features of normal walking. And I'm just looking, of course, at the knee and the ankle, because that's what we're replacing. So you have first heel strike, which he's doing in these phases of gait. And then heel strike, basically what the leg's doing is absorbing shock to some extent. You hit the ground, and your ankle flexes downward toward the ground, and your knee flexes also. And what that does, again, mostly is absorb shock, but also keeps your foot from slipping on the ground, or it reduces the likelihood that your foot's going to slip because there's less, essentially, shock on it. And then in mid-stance, you can see here his knee is flexed here in mid-stance, and it's flexed because if my knee is straight, then I kind of have to vault over it, and my center of mass or my body kind of goes up higher than it needs to go. So one flexes your knee in mid-stance. In late stance, you extend your knee here, and that's also because otherwise your body mass would go, the center of mass would go lower than it needs to go. So your body's center of mass goes up and down and up and down, but by doing this slight flexion and then this extension, then it doesn't go up and down as much as it otherwise would, as much as it does in an amputee, for example. Also in late stance, you push off with your ankle, and that propels the body mass forward and also gets this leg swinging forward to take the next step. So then in swing, the knee flexes first and then extends, and then ankle, basically you pull your toes up a little bit. It's called ankle dorsiflexion, so you don't stumble, you don't stub your toe on the ground quite as much. So that's I think some of the major things going on in normal level walking. That's that. Okay, so if you look at an amputee walking with one of those state-of-the-art prostheses, this is a guy that's a subject for a lot of our experiments. He has actually that exact same prosthesis on, just he has got this plastic cover on it. But heel strike, basically, he doesn't get any knee flexion or any ankle flexion. So the leg doesn't do any shock absorption for him. Mid-stance, he gets no knee flexion. If his knee flexes while he's in stance, then he just goes down. Right, he's got to keep it locked, and he keeps it locked because there's that stop, and he uses his hip torque and really pushes backwards on his hip so the knee doesn't unbuckle. And so he's not getting that benefit. Late stance, he's not getting any push-off, so he has to work a lot harder with his hip to swing the leg forward. And then also he's not getting any ankle dorsiflexion here, so his toe is much more likely to stub the ground. So he's really not getting any of those salient features, although he is getting, the knee is flexing and extending in swing, so he's getting that one. Okay, so we have to figure out a way, if we have a powered leg, to have it do in a natural way, in a reliable way, all the things that a natural leg, a normal leg would do. And I tried to condense a whole bunch of information in this one slide, so because it's easier to show things through videos and whatnot. So I'm glossing over some things technically here. But this is what we do, is we divide that walking cycle into naturally occurring distinct behaviors, which happens to be 5. And I won't go into it, but mathematically we can decompose what's normal biomechanical data into different behaviors. And so in doing that mathematically, we get 5 behaviors. And so each of these little bubbles, which we call a phase, is one of those behaviors. And if we just switch basically we have all the sensors on the leg, and what we do is just use the natural cues a person would give it in normal walking to switch from one phase to the other. So let me just give an example. It's the easiest way to do it. Is that when my leg is swinging, it has one kind of neuromuscular behavior, but as soon as it hits the ground and heel strike, everything stiffens up. It's a different neuromuscular behavior. And that heel strike I can easily detect because I have a sensor on the heel. So that would be this one right here. We switch from this behavior to this behavior just from heel strike, and that's something the person doesn't have to think about. They do it naturally. As far as, let's say, going to push off, this is late stance. This is when the ankle pushes off to do this. That's a different behavior. And the leg, the natural cue that's given by the person is when I reach forward with my other leg, then my ankle angle gets to some point that means I want to start pushing off. So these are all natural cues the person doesn't have to think about. And by doing this effectively, what we get is, because we've programmed it with these natural neuromuscular behaviors, we get what's called matched impedance, which basically means that the leg feels natural to the person and they walk in a more symmetric way. So without maybe explaining that much more, this is called, in engineering parlance, a finite state controller. And inside each of these things, in engineering parlance, it's called an impedance controller. But so without going into that, I'll just show you this video, which I probably need to go over here to start. And so this shows a subject walking at 3 different speeds, and first in regular motion and then in slow motion, just for like a stride and a half or something. This is the slow walking. And so you can start to see, in slow actually you do get those features. It's easier to see in the self-selected and fast, so I'll wait for that. And I'll point it out in the slow motion version of self-selected. So this is self-selected speed. So if we go slow motion, what you can see is here, ankle and knee flex for shock absorption, knees flexed in mid-stance, knee extends, ankle pushes off, ankle dorsiflexes as it goes through. So you're getting all those things. This is a fast cadence. You're getting all the things that were the salient features of healthy biomechanical gait. So let's see. Okay, so what we did then, I got to start this one too, is compare we compared the state-of-the-art prosthesis, which is this first one, to our prosthesis, to healthy subject data. So now I'm going to show this in terms of data, but I'll explain this because it's not as complicated as it may look. Okay, start with this middle plot here. This is for the knee and the ankle. This is the knee joint angle for one stride. So this is heel strike for another heel strike. And what we did is took a bunch of steps and just overlaid them on one another and averaged them. And this is the same for the ankle. So this is healthy biomechanics at 3 different speeds, slow, self-selected, and fast. And this is what it looks like. This is the little dip in mid-stance. This is the knee flexing during swing. This is the ankle at heel strike, kind of flexing toward the ground. This is the ankle at push-off. Okay? So this is healthy biomechanics. If you look up here, this is what our leg provides. So you can see here and here the same kind of, here's the mid-stance, knee flexion. This is knee flexion during swing. This is ankle plantar flexion at heel strike, and this is push-off, ankle plantar flexion at push-off. So we're getting something, if you compare these two and these two, then you see that they have the same salient features. If you look at the bottom, this is that state-of-the-art leg. By the way, this thing is some of this has to do with our healthcare system in the U.S., but this is about a $60,000 leg, the state-of-the-art one. You get no knee flexion, essentially, during stance. You do get a knee flexion during swing. Incidentally, it doesn't actually look like these two things. The properties are different at the 3 different speeds. And the ankle, you get almost nothing at heel strike, and you get essentially nothing at push-off as well. So we're able to then reproduce, apparently, a much closer approximation of healthy biomechanics relative to the state-of-the-art. So that's fine, but what are the benefits of that? What are the net effects of that? So this is his daily use prosthesis. He walks when you just tell him to walk at a self-selected speed, he walks about 4 kilometers an hour. With ours, when you just say walk whatever feels comfortable, he walks at a little over 5 kilometers per hour. So he's walking faster, 25% faster with this leg than that one. The reason for that is actually he takes fairly symmetric steps with these two legs, because this pushes itself off and propels itself forward, whereas he takes much shorter steps with this leg than with his sound leg here. As far as energy goes, I mentioned the other things that amputees expend more energy. We went to, did some treadmill testing, and on the treadmill, the way that most people do these comparisons is they subtract out the metabolic baseline. So if you subtract out the metabolic baseline, have him walk on a treadmill and measure the oxygen, his rate of oxygen consumption, then he uses about 39% more energy consumption walking with that state-of-the-art commercial prosthesis than he does with the powered prosthesis. Okay? And that makes sense for lots of reasons. One is we have better biomechanics. For instance, when he doesn't have that shock absorption with this leg, that's energy loss. So his efficiency is lower than this. The other reason is that this is actually contributing energy to him. It's got batteries on it, and the batteries are slowly being drained by the motors, which is helping push him forward. So he's got something else there doing work for him. I keep forgetting I don't have to go to my computer to change the slide. Let's see. Okay, so some other things we do. The leg, one of the real constraints or limitations of state-of-the-art legs is their inability to adapt. Level walking is fine. That's what we do when we're on a hallway. But if you go outside, like tomorrow at graduation, the ground's not going to be perfectly level, and obviously there's uphills and downhills and stairs, and we do all kinds of different things. And so we looked at lots of different activities. This shows sloped walking. So this is the same. Here's knee data, ankle data, again heel strike to heel strike. This is healthy subject at different slopes. This happens to be up slopes, because if I put the down slopes on, it all gets too much information. So the level is the blue is what I was showing before, and then as you climb steeper and steeper slopes, what happens, and this makes sense, pretend instead of a stair this is a slope. When I do heel strike, my knee is bent because I'm lifting my leg up, and yet on the leg that's in the back, the knee is not bent, it's straight. So this is what you're seeing here. As I go up steeper and steeper slopes, we'll look at it over here. At heel strike, the knee is bent more and more and more. But here, when I'm pushing off, the knee is always just about straight. And the ankle, similar kind of thing, except for the ankle angle. As I go uphill, my ankle is obviously going to bend back more and more because it wants to keep my body in line with gravity. So this is another behavior that we want to implement. And this shows, the next slide is a better illustration of this, so bear with me on this one. All this is to say is that here's the healthy biomechanics. This is what our leg is doing, which looks a lot like that and a lot like that. And this is what his $60,000 leg is doing, which doesn't really look like either of these things. There's no real adaptation here, right? It doesn't matter how steep a hill he goes up, his ankle's going to stay at about that angle. And his knee is it's got to be straight when he hits the ground. If his knee's not straight when he hits the ground, then he hits the ground because the knee's going to buckle. So the easier way to see this data is probably here. And I'm going to start with the bottom sequence, which is him walking with his C leg. Now he took the plastic cover off, so you can see it looks a little bit more like that other one that I showed. So he's walking up a 10 degrees grade right here. And here, I can't see it that well. Okay, his leg is straight. This is during push-off, but he's not really getting any push-off because the leg doesn't contribute power to him. So if you can see here, he's up on his sound leg, up on his toes. Here's the slope of the ground. Here's the slope of his shoe. And he's got to be up on his toes because this leg's not going to swing forward enough. It's not pushing itself off. He's got to swing it with his other hip. And it doesn't get high enough. And if he doesn't do this, it's going to scrape the ground. So he's going to stumble on it. And then when he brings it forward, again, he's got to land with a straight leg, because if he doesn't land with a straight leg, the knee will buckle. So and you can see, look how high he is on this other toe back here. So he's really compensating for lack of the power in the leg in other ways. If you look at our leg, here you're getting this full powered push-off. So his leg is flat on the ground here, his stance leg, because he doesn't have to worry about it not swinging high enough. And then when he hits the ground, he can hit with the knee bent at an angle there, and so he's not having to do, he's kind of pushing off here, but he's not having to compensate in other strange ways, and he can take a bigger stride also. So basically in the uphill also we're able to do restore what we consider to be fairly healthy biomechanics. Let's see, power consumption. This is one of the things that we didn't know when we proposed this. When we started working on this in about 2005, what we said is, hey, it looks like technology is getting to the point, based on our back-of-the-envelope calculations, that we can make a leg that's powerful enough and light enough to make this happen. And so we want to build the leg. Here's our ideas for the controllers, and we believe a battery, given the advances in batteries, will be good enough to last all day. But we didn't, so we conjectured that. We gave some information, calculations to support it, but now we're doing the work to really support it. So this was an uncertainty, whether or not the battery will last a full day. And what we find is, and actually our numbers are even better now, but basically this leg, he can take 14,000 steps level walking on a battery charge, which is equivalent to 13 kilometers of walking, which most people are not going to do in a day. He can take 11,000 steps up a 5-degree slope or about 9,000 up a 10-degree slope. So an active, healthy individual takes between 7,000 and 13,000 steps a day. So if an amputee were walking as much as an active, healthy individual, then you'd have a full day of walking on one charge. And then when you go to sleep at night, you plug your leg in and it recharges. As I mentioned before, amputees generally take 2,000 to 3,000 steps per day because they're just not as mobile. We hope with this technology they become more mobile, but even if they become as mobile as an active adult, the battery is still will last a whole day. So that was one of our objectives, and originally an uncertainty. Okay, so yeah. Yeah, it's not this, but the.
But I mean, is it the size that they've been able to have more power in a smaller?
Oh yeah, it's more energy in a smaller package, and that market has been driven by, 10 years ago, if you asked me about batteries, I would have given you a really pessimistic spiel. But because of cell phones, laptop computers, and even more so the hybrid and electric vehicles, there's been a big push for significant improvements in batteries. So battery technology was improving at a pretty mild slope for about 20 to 30 years, from about the 70s through much of the mid-90s, we'll call it 20 years. And then from mid-90s to late 90s through now, just the last decade and a half, just really has picked up a lot and has made this doable. Because if you can walk for 20 minutes on a charge, nobody's going to, that's not useful to me as an amputee. So these battery technology is part of, when I talked about the different types of technologies that have gotten much better to enable this, battery is a big one. Rare earth magnet brushless motors is another big one. The microelectronics is another big one. The computer that we use, I call it a computer, it's the size of a stamp, and it consumes 400 milliwatts. That doesn't mean a lot to that many people, but it has the same computational capability of a chip that 15 years ago would have consumed 100 times that much power. And that in and of itself would be enough to make this not doable. But all these things have come together, and so it's kind of exciting for somebody who does what I do, because it enables really a lot of new things. But the battery we're using is called a lithium polymer battery. Ours weighs about 1.5 pounds. It's one of the heavier components in the leg, and it's embedded inside the structure of the leg. So you have to take off some. You have to take off an aluminum cover in order to get to it. So it's kind of part of the structure. But yes.
How does that? It's a stupid question, but yes. What is it about that leg that's $60,000?
That's tomorrow's lecture.
Yeah, really. That's a U.S. healthcare system lecture. It's not that there is technology. In that other one, there's some advanced technology in it for sure. There are also clinicians that have to fit it to the amputee and have to train the amputee to walk on it. So that's part of the cost. And then other parts of the cost, in my opinion, have to do with the market, I guess I'll say. Those aren't great answers. I'm starting to learn some about this, because a lot of what I did was research. Now, actually, there are companies who are interested in licensing the work, both in lower and upper extremity prostheses that I'm explaining to you, and I'm learning some about the market. But some of it is based on what you can get for it, as opposed to what it needs to be. That's my opinion.
What adjustments, if any, do you make for starting from a standing start and then stopping?
Yeah, that's a good question. So actually, that's my slide here. So maybe I'll get to that. I'll get to that now.
What will the biomechanically cost if the state-of-the-art costs $60,000?
Yeah. I guess I'll say this. It will cost more than that, but it doesn't fundamentally have to cost more than that. it's kind of what the market will bear kind of thing. That's not my, it's getting a little bit beyond where what I
Start with the materials and forget about all the drawings.
Start with the materials, yeah, okay. So the material cost is not a lot more than the other. When we make prototypes, we pay about $10,000 a piece for a prototype. So if that, but those, we're not leveraging any large-scale manufacturing to do that. Those are one at a time types of fabrication costs. At any rate, so okay, I will. I like discussing that, but so maybe after, I think is a good time to do it, and we can talk about the hand cost too. Okay, so there was the question about how you transition from standing to walking or whatnot. What a leg does is a lot of different things, and what I'm doing now is obviously not walking, but it's not completely standing either. I'm kind of shifting my weight around. That's what we call standing. You also, of course, transition from standing to sitting, sitting to standing. You go from standing to walking. You walk at different speeds, at different slopes, and then also the other major activity that you do is stair ascent and descent, and going up or down a curb would be a subset of that. I don't have that shown on this picture, but we have these. I explained the walking controller. I didn't do a great job explaining it, but I explained essentially how we do that. We have similar controllers for each activity, and we have a stair ascent and descent controller that we're testing right now. That's not shown here, but you need to know when to switch between these things. And again, you don't have any way of connecting to the person, and to us, it doesn't make sense to have a person push buttons on the side of their leg when they want to change things. We should be able to recognize, in a sense, when the person wants to do something. So we have developed a control structure where this is kind of all those other little controllers. And what we have here is what we call an activity mode recognizer. And this is a pattern recognizer. It looks at patterns. It's kind of like there's a lot of programs now that do voice recognition and handwriting recognition and whatnot. This is a similar kind of thing, but it's looking not at your voice and trying to figure out words, and not at your handwriting and trying to figure out what letters you want, but it's looking at patterns in what you're doing and all the sensor information and what that means as far as what you intend to do. So this, again, is a one-slide kind of condensation of how we do it, and I'll try to gloss over it a little bit. But we take all of our sensor information. We've got a lot of sensors on this thing. And we have a person do a certain amount of activity. Let's say level walking, or let's say he just standing around, or let's say transitioning from standing to sit. And we record that information, and we kind of massage it down to a limit, so it fits in 3 dimensions here. And if you can see here, this is kind of hard to see, but this green is what we get when the person is walking around. At any given time, the patterns that he does can all be kind of massaged down to this cloud. And when he's standing, it's the black cloud. And when he's sitting or transitioning from standing to sit, it's the red cloud. We can then take those clouds and fit probabilistic models to it. So these are mathematical models. They're probabilistic models. So they don't end where those shapes end. They go on forever, but those shapes mean a certain probability. And so we then take those models, take all the data, and 100 times a second while a person's wearing the leg or doing whatever, it's always checking the probability that he or she is doing a given activity. And if he or she is sitting, and then we get at 100 times a second about 20 decisions that say, well, this person wants to stand now, the probability is highest that he or she wants to stand, then we shift into that controller. So this is called real-time intent recognition. And I'll show you a video here. I show this we have this video also just kind of out and about, but I like it on the treadmill because you can clearly see he's punching keys to change his activity, and then it's just clear to see when his activity changes. So he'll walk, he'll stop it, and then the leg decides he wants to stop, and it goes into standing. When he starts sitting, so this has to happen real quickly, because if he wants to sit and it doesn't let him sit, then it's awkward for him. So it has to figure out within a couple hundred milliseconds what he wants to do. So now he's just kind of shifting his weight around, which is standing, and it's distinct from walking, which is locomoting. And then after he does that for a little bit, he'll start it up again. if you probably didn't notice, but last time he started with his prosthetic leg first. This time he started with his sound leg first, so he can do either one of those things. But this way, it again kind of uses these direct cues when he's inside of a mode to switch from phase to phase to different neuromuscular behaviors. But when he's switching between modes, between different activities, it's using patterns in what he's doing. So we, by the way, have really done almost all of our experiments on a single subject, although we started a second subject about 3 or 4 weeks ago, so we're starting to get more data on another subject. One of the things that I think is, that excites me about this device is, I mentioned before this falling, and there was a study done in 2001 on 500 amputees, and the conclusion was falling and fear of falling are pervasive among amputees. I mentioned also before in a different study, also a large number of amputees, that the rate of falling is similar to institution living elderly, and the rate of seeking medical attention is similar, and it's worse in younger people than older people. As far as why people fall, there's multiple reasons, but one, as I've already shown, there's a lack of healthy biomechanics. The biomechanics we do for lots of reasons, for efficiency, but also for stability and robustness. And if you don't have those healthy biomechanics, then you increase the likelihood of a stumble. In these people, in these amputees, if they stumble, they don't have these recovery reflexes. So if I'm walking across campus and texting on my phone, which I don't do because I don't know how to text, but and I stumble on a curve, then I have this natural reflex to lift my leg up and put it in front of me and keep myself from face planting. And an amputee doesn't have that reflex, doesn't have that capability. But again, we have this powered prosthesis. It's got sensors, it's got kind of a brain, a computer, and it's got motors so it can react. So we can, if a person, number one, we hope by restoring healthy biomechanics, we decrease the likelihood of a stumble. But secondly, if a person does stumble, we are working on implementing recovery reflexes so that we decrease the likelihood of a fall. This is a video. When you stumble, there's 2 strategies you generally take, an elevating or lowering strategy. The one is picking your leg up over. Oh, this isn't on an amputee. This is on healthy subjects in our lab. Okay, what we did, hopefully, this didn't show up really well. So there's this little curve we have that pops up and locks, so we can make people stumble. See what's going to come up right there. This is elevating. He pulls his leg up over and keeps himself from face planting there. The second one shows a lowering response. So this is actually earlier in swing. When you hit something, you just decide, go ahead and put your foot down and use the other leg to hop over. So this one, here, hit the object, put your foot down, and use the other leg to get over it. So we are working on, and we have some preliminary work here, but I wasn't going to show it. I just wanted to kind of point to where we're going with this now. In order to do this successfully, you have to be able to very quickly detect that you've stumbled. You have to make the right decision in that should you lower the leg or elevate the leg, and if you make the wrong decision, you potentially make things worse. And then once you make the right decision, you have to provide the control commands to the knee and the ankle to do the right thing. So that's what we're working on now. We just today got what's called IRB approval to basically make amputees stumble. IRB approval is basically what is human subjects safety board, so you have to put everything through them. So when we do that, the person wears a harness, safety harness and all that. We're very cautious. So as far as the leg work goes, well, anyway, that's one of the things we're doing. I think that's potentially exciting because that, restoring natural, improving mobility, quality of life, that's something that's important to me. But you start talking about decreasing falls, and then you can start talking about paying back for the additional upfront costs of this in a different way, if you know what I mean. It's not just quality of life, but you're preventing, presumably, injuries from happening. So summary, we were able to provide the essential biomechanics of healthy gait. We showed all this right now on a single subject, that we've lowered metabolic energy consumption, we've increased self-selected walking speed, and we have enough battery to go a full day between charges. Currently, we're doing stair climbing descent. When I say currently, this is going on today. And And then also we are currently implementing the stumble recovery responses, which will be going on this month. So that's some of kind of where we are at within the lower limb work. And as I mentioned, I was going to use about 2/3 of my talk for upper, and then maybe now less than 1/3 of a talk about lower limb, and then the rest about upper extremity. So we're also working on upper extremity. It's a real different kind of problem, although the limitations of the state of the art are probably comparable, maybe even worse than upper extremity. I'd say worse, probably. Well, it's hard to say. There's two major types if you look at the commercial state of the art in upper extremity, and I'm going to talk just about hand prostheses right now. The first type is up here, this body-powered prostheses, and this seems maybe to some people archaic, but this is really, the majority of amputees use this. It's kind of World War II technology, but still, is, for various reasons, very effective. What it is you wear a harness on your shoulders. There's a cable that goes across, usually it goes across, sometimes it doesn't, but you kind of shrug your shoulders and it pulls that cable, and pulling the cable opens that hook. These are lower cost and robust, and there's other reasons why people like to wear them. Some problems are that you can't really, people complain about the harnesses, and you can't really use your arm over your head. Because if you lift your shoulder up like this, I can't open it up anymore. So you have a restricted range of motion where you can use it. There's another type that's higher tech called myoelectric prostheses. And for these, when any of us contract our muscles, the muscles give off an electrical signal. And you can put a little electrode on the surface of the skin and pick up that signal, and you can pick up a signal that's in proportion to how strong you're making that contraction. So for these, you have the same kind of socket that you wear on your lower limb, but it's on your upper limb. You put a little electrode here, and you put one here, and when I contract this muscle, I can send that electrical signal to a motor, which makes the hand open, and when I contract this muscle, I send a signal to the electrical motor, makes the hand close. So you have these hands that look like they have multiple fingers, but they're really just pinchers. They can open and close. They can't move fingers independently. And some people just choose, instead of looking like a hand, just use something that looks like a pincher. Both of the, and this you can use, you can put it over your head and use it or whatever. There's no range of motion restriction, and you don't wear a harness like that. So people like this for different reasons. You can't get these wet generally, so depending on what you're doing, you might want to use one versus the other. But both of these are single degree of freedom devices, which means they're basically pinchers. Which is obviously you're losing a lot of functionality relative to what a native hand can do, which has something like 19 degrees of freedom in it, depending on how you count things. Now, I mentioned before this advances in robotics technology has driven, this is very recent, but have driven a lot of people to start looking at multi-fingered hands. This is a German company, Otto. This is multi-fingered, but it really, it's still just grasp, but it can either grasp this way or this way. So this is a lateral grasp, and this is a kind of a palmar grasp. This is a Scottish company called, or maybe it's Welsh, I can't remember, Touch Bionics. This actually has, each finger can move itself, and the thumb can move in one direction, but what you do is kind of manually reposition the fingers, and it can do different grasps, but you have to manually position it into different places first. This is a hand made by DECA, who are the same people who make the Segway, and they were funded by DARPA, a defense agency, to make one of these. But and we have also, now there are issues with all of these, which I'll get to later, so they're not really ready for prime time, so to speak. But we also are making, have developed a hand. This is ours. This has 4 motors, 1, 2, 3, 4, kind of buried in these would be the carpal bones, or metacarpal bones in the hand. We designed it to be able to do 8 different grasps, and we call these canonical grasps. And we figure if you can do these 8 grasps and all the motions in between, then you can do most of what you need to do in activities of daily living. So cylindrical, lateral, also called key grasp, tripod, 3 fingers here, hook grasp like carrying a briefcase, pointing for punching buttons and whatever, a tip grasp, platform is just holding a plate or something, and spherical. So our hand. Again, this is kind of this is a computer model, so we don't have a glass hand, but this shows how the motors lie in the palm. This one shows the same thing, so it's really well integrated. We use some manufacturing processes called additive manufacturing, which have really only been around in the quality in which we use them for a year or two.
What kind of manufacturing is that?
Oh, additive manufacturing? It's basically it's really good rapid prototyping. So rapid prototyping for a long time was prototyping. But now the strength of materials and the resolution and the costs are such that people have started calling it additive manufacturing. Instead of subtractive, like what you normally do using drills and mills and lathes and whatever. Instead of taking material away, you build up the material from nothing. Okay, this is not that important. This is some characterization. The only point to bring away from this is that this has speeds and forces that are representative based on biomechanical handbooks, representative of what people do in activities of daily living. So the hands, they're not super strong, but they're strong enough to do the kinds of things you need to do for most activities of daily living. This is a video. Oh, yeah, okay, I don't have to start it. This shows some of that hand working. I'll kind of, to some extent, use my time while this is running to say that building these to work effectively and have biomechanical levels of force and speed is half of the problem, but how to interface them with the human body and control them in such a way that a person can really use them to do activities of daily living, that's the other half of the problem, and that may well be more than half the problem. So all those hands that I showed before these other companies are making, and including us, none of these are going to be useful unless we have a way to interface them with the person so that they can control them in an effective way. So that's the other part of what we're working on is control. Now, we're not the only ones working on it, so I'm going to mention briefly what some other people are doing. The real vision everybody has is kind of the bionic thing, which is integrating these robotic systems into the body. And that may happen at some point. But right now, a lot of that technology, this what we call neural integration, is not really at the point where it's effective enough to use. But nonetheless, let me outline some of it. This is a so let me say also, in the leg engages in basically patterned activities. We can use pattern recognizers and whatnot, and we can use those what are called finite state machines to reproduce walking and stair climbing and so on. But the hand is not like that. It's not periodic. I can't look at patterns in what I'm doing and predict what it is I want to do with my hand. So it has to be interfaced in a much more direct way with the brain, with intent, a direct channel to intent. So this is some of the way people are looking at it, neural interfacing. And there are some groups around the country and around the world looking at what are called cortical implants. These pictures are from John Donahue's group at Brown, and they have a spin-off company called Cyberkinetics, and there are other people who do this as well. But they're talking about getting little electrodes like this. This is about 3 millimeters by 3 millimeters by probably 1 or 1.5 millimeters. And implanting these in the motor cortex of the brain. You can see a CAT scan with the chip in this guy's name was Matt Nagel, in his brain. So they try to put it in the right place and then train the subject. The brain's pretty plastic, so you can train somebody, and he can think that he wants something to move, and that will generate enough signals on these electrodes so that they can make something move. So that sounds interesting. It's obviously very invasive, but right now it's just the level of accuracy, bandwidth, so speed that they have and repeatability are nowhere near good enough to operate a hand. So this is interesting, but a long way from being used, in my opinion. This is a similar idea, but instead of implanting in the brain, you implant in the peripheral nerve. So this is a picture from a group at University of Utah, a guy named Richard Norman and Greg Clark. And they're trying to do, again, something similar. But this, in some senses, is also harder. It's hard, actually, probably mostly for mechanical reasons, in that the brain doesn't move around a lot, but when you have a peripheral nerve, you have muscles moving all around, and it takes this thing and moves it all around and makes the problem that much worse. So this also is not yet ready for prime time, but interesting work. There's another group, actually some people that we work with at the Rehabilitation Institute of Chicago. They're doing something kind of halfway in between where the nerve, actually, it's hard to measure an electrical signal in the nerve because the signals are so small. But then it goes to the muscle, and the muscle actually amplifies that signal. So what this is Todd Kiken, who's a physician at RIC. He takes the muscles in the residual limb, in this case they're the pectoralis muscles because this is called a shoulder disarticulation, but whatever the most distal muscles are, he separates them because they're not really doing anything anymore. He separates them. He takes the nerves that used to go down to the hand, separates them, sutures one of those nerves into each muscle and uses the muscles as an amplifier, and then picks up those signals from EMG. So it's also something that has promise, but it's not yet ready for prime time. So we're doing something that we want, the work in my lab, we want to be able to translate. If it's something that's going to improve quality of life for people, we want it to be able to translate into a commercial market in some reasonable time frame. So we're using surface EMG. Instead of just 2 EMG electrodes as are used in commercial prostheses, we're using 4. We use the pattern recognition to take those 4 electrodes and break it down into 4 different signals. And we use those signals to this seems kind of strange, but kind of drive the hand around a map. And what we can do, the reason why we do that is because we can get to any hand position with just one of those 4 signals. We just need a directional signal here and a directional signal here. So it's a way of breaking up the complex function of the hand into a much more simple, to tie it all together with a fairly simple map. So I'll show you a video. This one I probably have to start as well. Now we're not using EMG to drive this video. We're using we are using only 4 inputs. And so the first time it's going to go through too quickly and you won't be able to see it. But here's the map. Here's the 4 inputs. Here's the hand that's driving. The only thing to look at the first time is that you can move it in real time and you can achieve these different postures. And then it's going to go through in slow motion. Maybe you can see a little bit more. So the point is here, 4 signals, 1, 2, 3, 4. You're going to drive kind of up the map this way. You want to get to this posture. You drive up the map here with that 1 signal. You take a right, which is this signal, and you're in that. That's called a lateral or key grasp. Now you go back to platform, and this next time it's going to go up to point, and then you're going to go over to a tip grasp, and then go back. The point here is that we're trying to combine information of the configuration of the hand with information from the EMG and use those together again in a map so that you can, from a limited number of input signals, control a fairly high degree of freedom space, which would be the space you need to operate a hand for activities of daily living. So this is work that is in, it's in progress. So I don't yet have an amputee using it, but kind of as a summary of that, one of the things we're doing that's very important, this is the skeleton. We're molding a silicone-based flesh cover, which is an important part of it because your interaction with the world has a lot to do with kind of that soft tissue. And this should be done probably in the next week. And we're integrating EMG to drive that topographic control that I mentioned before. And other things that we want to do, obviously we want to put it on an amputee, and we're heading in that direction. And this, unlike the leg, right now the electronics are off-board, and we'll integrate the electronics and battery into a self-contained device. We want to design and integrate a wrist at some point, and then also this has to do with implementing force feedback, is that when an amputee squeezes something, they don't really know how tightly they're squeezing it, and we have we're developing some methods to give them that feedback so they know how tightly they're squeezing it. So I think that's all that I had. Yep.